silicon precursors. And we will combine the monomer plus, that was too short to see, the monomer with the inorganic already preformed phase and perform the polymerization in situ, or use the PLA and generate in situ the silicon-rich phase, or use the lactide and generate in situ the inorganic phase and polymerize at the same time. So the scheme will be, the content will be this one, describing the three levels. So coming back to PLA, the PLA will be polymerized to get high monomer PLA from pure lactide, in our case L-lactide, and ring opening polymerization. The second, for the inorganic phase, we will use preformed nanofiller as fumed silica, hydrophilic or hydrophobic, with different specific surface. I will describe just a few of them, and or hydrophobic silica modified with short chain, hydrophobic short chain, in order to get different interaction with the medium, PLA or monomer. And the surface functional and also surface functionalized silica, the same, with 200 meters square per gram, modified with a metacrylate or modified with an hydroxy-terminated silane. And this one will be interesting because we can expect some ring opening polymerization from the silica surface in order to graft in situ, to make some grafting from in situ during the system. And we will go to low amount of inorganic rich of about 5% by weight. Silane, in which we have a metacrylate group or an amine group, which could be co-hydrolyzed and condensed with the others. And we'll use also this one, which is a pre-condensed, the general formula of pre-condensed precursors with dietoxy system, polydietoxy system. So in that kind of chemistry, you have a release of ethanol if you have a toxic group, or methanol if you have methoxic group, and you have also the need of water, which could be of interest, of course, and cause no problem for coatings, but for bulk applications it could be something to avoid. So we look at the literature, and there is only few papers about the non-hydrolytic sol gel chemistry, which is, for me, more complicated, and quite complicated even seems as you perform that kind of chemistry, but you can do that and combining chlorosilane with netoxy or methoxysilane. And using a catalyst, we will see we can have directly also the silicon-rich inorganic structure, and for both we target 5% equivalent SiO2 by weight. So let's look to the different way we can, so combining polymer and sol gel, polymer plus fumed silica, monomer with sol gel, and etc., all the combination. So let's look to the first, which is the polymerization of lactide, so the monomer, in the presence of fumed silica. So we go from a suspension of silica, fumed silica, into a lactide, and if we look to the chemiorheology, which is the viscosity as function of time at a given frequency. If you look at different temperature, you have a signature of the polymerization, which means that the viscosity increase. For example, here 165 degrees Celsius, and of course with a higher temperature of reaction, so isothermal polymerization, you have a faster curing and a faster growth of the polymer. So if you look to that, into those three first case, high temperature, you have something which looks as a viscoelastic fluid. And if you perform the polymerization below the crystallization temperature of PLA, as the lactide polymerized, the polylactide is formed and then crystallized. So you have an increase of the viscosity due to the fact that you generate in situ also the crystallites of the PLA. So that's the L-lactide alone. So now we put the lactide with silica, and so that's the same G prime and G double prime for a given temperature of reaction, which is above the crystallization temperature. So G double prime, G prime for the pure lactide. So again, the increase of the viscosity of the shear modulus and the loss modulus here. And if you look to the lactide plus 5% of silica, you can see that now the G prime is above the G double prime even from the beginning, which means that the suspension of fumed silica is already in lactide is already a gel. So you polymerize the lactide into a gel structure, which is you can retrieve, of course, at the end of the reaction looking to the rheological behavior of the nanocomposites. So that's one of the problems of processing of those systems, because if you put fumed silica, even 5% of a low surface, specific surface silica, you have already a gel, which is sometimes a problem to process. Now, if we change the functionalization of the silica, so the interaction in between particles, the gel is not formed at the same level. So if you look now to, again, the pure lactide, here you have the fumed silica, 5% with methacrylate modified. Now you have a gel which is not so strong, and the system goes like that. So the G double prime at the end is all above the G prime, which means that the system remains as a viscoelastic fluid and behave as a thermoplastic system, which is again shown by the rheology of the PLA fumed silica at the end of the reaction. So we changed completely the way, and we were able to process PLA 5% silica for a given specific surface by changing the interaction in between particles. So the surface property, the surface chemistry of the silica is very important to be able to process the system. So in all of the case, so for PLA, pure PLA, so pure lactide polymerized here. Here, but the polylactide polymerized with a system which is fully modified with the hydrophobic chain, or half modified with the hydrophobic chain, we were able to get quite nice molar mass, but that was even better with the PLA methacrylate and the possibilities to process. So in terms of practical things, this kind of surface treatment is preferable to those ones. And if we look to this one, which is a very interesting silica, modified with an hydroxyl-terminated silane, polymerized in the presence of lactide, the lactide polymerized, but also grafted onto the surface. And the generated chain onto the surface are not so nice compared to the neat PLA, so the chain form into the bulk, but you are able to graft chain, you have a grafting